Good morning. Myself, Dr. Kuncham Narasimhulu, Assistant Professor of Physics, SSA Government First Aid College, Autonomous, Ballari. Let's today discuss about conservation laws in Kepler laws and second law of planetary motion. In our solar system, Sun is surrounded by the planets which revolve around it. The planets do not emit light but can reflect it. There are objects which revolve about the planets. We call them satellites. The moon is a satellite of the Earth, a planet which revolves about the sun. In addition, there are artificial satellites which are man-made and which can revolve about the planets or their satellites. The path of the planet or satellite is called its orbit. What is Kepler laws of planetary motion? Johannes Kepler was one of the greatest astronomers of all times. He was the first scientist to formulate three fundamental laws of planetary motion. There are Kepler's first law. The law is nothing but law of orbits. The path of the planets about the sun is elliptical shape with the center of the sun being located at a focus. Kepler's second law of motion is known as law of areas, equal areas. An imaginary line drawn from the center of the sun to the center of the planet will sweep out equal areas in equal interval of time. Last one, the Kepler's third law, the law of period. The ratio of square of the periods of any two planets is equal to the ratio of cubes of this average distance from the sun. Let's discuss about one by one. Kepler's first law of motion. According to Kepler's first law, all the planets revolve around the sun, elliptical orbits, not a circular orbits. The sun being one of the foci of the ellipse. An ellipse is a figure obtained by cutting a cylinder with a slanting plane. This is known as the law of orbits. What is Kepler's second law? According to Kepler's second law states that the radius vector drawn from the sun to the planet sweeps out equal areas in equal intervals of time. This law shows that the velocity of a planet as it revolves around the sun varies according to its distance from the sun. Whenever it travels more quickly and it moves further away, its speed shown down. As the orbit is not a circular, the planet's kinetic energy is not a constant in its path. It has more kinetic energy near perihelion and less kinetic energy near aphelion. Implies more speed at perihelion and less speed at aphelion. So, suppose a planet P is moving an elliptical orbit as shown in figure. It moves from P to P dash in a small time dt. The area swept out by the radius vector is the area of the figure S P P dash. If dt is a infinitesimal small, P P dash is a straight line, that is r d theta, and S P P dash is a triangle. You see that the area of that triangle SPP dash is equal to dA, that equal to half r into r d theta, that is equal to half r square d theta. Area velocity is the area swept out per unit time by the particle moving along a curve. That is, area velocity is dA by dt is equal to half r square d theta by dt. But r square d theta by dt is equal to h, that is a constant. Thus, dA by dt is equal to a by h, that is equal to a constant. Kepler's second law states that the aerial velocity of a planet revolving around the sun in elliptical orbits remain constant, which implies the angular momentum of a planet remains constant. As the angular momentum is constant, all planetary motions are planar motions, which is direct consequence of central forces. And what is Kepler's third law? According to Kepler's law of periods, the square of the time period of revolution of planet around the sun in elliptical orbit is directly proportional to the cube of its semi-major axis. T square is proportional to a cube. Shorter the orbit of the planet around the sun, shorter time taken complete one revolution. Using the equation of Newton's law of equation, gravity and law of motion, Kepler's third law takes general form. P square is equal to 4 pi square by g into m1 plus m2 into a cube, where m1 and m2 are the mass of the orbits two orbits object in a solar masses.